Welcome to Dreaming Scientist's Sleepy Stories, a place where the mysteries of the universe guide you toward peaceful sleep. You rest inside a universe where nearly everything familiar is rare. The substance of your body, the breath moving quietly through your lungs, the matter beneath your feet, together they form only a thin trace of what exists. Almost all of reality lies beyond touch and sight. Roughly 95% of the cosmos is composed of two unseen components, known as dark matter and dark energy, neither of which shines, burns, or gathers into stars the way ordinary matter does. And yet, despite their invisibility, the universe depends on them. Without dark matter, galaxies would loosen and drift apart, unable to remain bound. Without dark energy, cosmic expansion would slow, reshaping the history written across the sky. These conclusions are not imagined or inferred loosely. They arise from measurements, patterns in ancient radiation captured by space observatories, vast maps of galaxies traced across billions of light-years, and mathematical models repeatedly tested against what telescopes observe. This story follows how those numbers emerged directly from the sky itself. It traces why gravity from visible matter fails when stretched across cosmic distances, and how dark matter and dark energy entered modern cosmology not as convenient ideas, but as results that could not be avoided. Every step rests on instruments, surveys, and observations compared carefully with the universe as it actually appears. The picture begins at the simplest question. Why does everything you have ever touched amount to less than 5% of reality? When cosmology becomes an exercise in balance, measured inputs checked against observable outcomes, the ordinary world shrinks into a minority role. Stars and planets, oceans and air, every element on the periodic table together form only a narrow slice. The remaining majority behaves unlike atoms. It does not glow. It does not clump into familiar forms. Yet it leaves clear traces in radiation, motion, and the slow growth of cosmic structure over immense spans of time. This conclusion does not rest on a single experiment or era. Multiple lines of evidence, each governed by different physical principles, arrive independently at the same composition. One comes from ancient light, another from gravity acting on motion, another from geometry encoded in how galaxies cluster across space. If any one of these paths could be explained using only ordinary matter, the story might end there. Instead, each one points in the same direction. The universe behaves as though most of its gravitating content is not made of atoms. Begin with the cosmic microwave background, the oldest light that can still be observed. It fills the sky almost uniformly, a faint thermal glow carrying subtle variations. Those variations are not random decoration. They are a preserved pattern formed when the universe was young, dense, and hot, and sound waves rippled through its plasma. Before atoms existed, space was filled with photons, electrons, and nuclei interacting constantly. Light could not travel freely. It scattered again and again from charged particles. As expansion cooled the universe, electrons eventually joined with protons to form neutral hydrogen. When free electrons faded away, photons were suddenly released, traveling unhindered across space. That moment occurred when the universe was roughly 380,000 years old, glowing at tens of thousands of degrees. Here is where this ancient light becomes an inventory of cosmic ingredients. The tiny temperature differences, measured in millionths of a degree, form a precise spectrum with peaks and valleys at specific angular scales. These features reflect pressure waves in the early universe, driven by radiation pushing outward and gravity pulling inward. The physics is simple and testable. Adjust the amount of ordinary matter, and the inertia of the photon-baryon mixture changes. Adjust the amount of non-atomic matter, and the depth of gravitational wells shifts. Each change leaves a calculable fingerprint. The Planck satellite measured this pattern across the entire sky with extraordinary precision. The result narrowed the range of possible cosmic compositions. In its final analyses, the collaboration reported tight constraints on both ordinary matter and cold dark matter within the standard cosmological framework. When those values are translated into today's universe, the familiar balance appears again. Atoms form only a small fraction. Dark matter accounts for roughly a quarter. Dark energy dominates the remainder. Earlier observations from NASA's WMAP mission tell the same story, expressed slightly differently but consistent within uncertainties. No matter how the numbers are presented, the conclusion holds. Ordinary matter is rare. At this point, a difficult question becomes unavoidable. What alternative could reproduce these precise radiation patterns without introducing unseen mass? Ordinary matter cannot be quietly increased. Because atoms interact with light, adding more would not only deepen gravity but alter how photons scatter. That change would distort the observed spectrum in ways the data does not allow. The early universe places a firm limit on how many atoms can exist. Even if one were tempted to ignore that limit, a second constraint appears later in cosmic history. The microwave background shows that early density variations were small. Over time, gravity must amplify those ripples into galaxies, clusters, and the vast cosmic web. Growth depends on matter falling into regions of slightly higher density. But in the early universe, ordinary matter remained tied to radiation, unable to collapse efficiently. Something else must have begun clumping earlier, something that did not interact with light, something that could quietly deepen gravitational wells while radiation still flowed freely. That unseen scaffolding allowed structure to form at the pace we observe today. And so, piece by piece, the universe reveals itself not through what shines, but through what shapes. You drift through a cosmos where absence carries weight, where what cannot be seen quietly holds everything together. The visible world is not diminished by this realization. It becomes more precious, a thin, luminous layer floating atop a much deeper reality. As this understanding settles, the universe grows calmer rather than stranger. Patterns replace mystery. Balance replaces confusion. And as you rest with this vast, quiet knowledge, the unseen majority of the cosmos holds its steady rhythm, guiding galaxies, shaping time, and carrying you gently toward sleep. Light resists collapse. Photons press outward, creating pressure that slows the gathering of matter, and for a long time this resistance keeps ordinary material from falling together easily. Only when the universe cools enough, when atoms can remain neutral, does familiar matter begin to move more freely under gravity's pull. If the cosmos contained nothing beyond atoms, there simply would not be enough time for the delicate ripples seen in early radiation to grow into the vast structures observed today. Something unseen must begin the process earlier. A form of matter that does not interact with light can start clumping while radiation still dominates, carving deeper gravitational valleys that later draw in gas. Stars and galaxies then form inside those invisible foundations. This is the role played by cold dark matter in the standard cosmological picture. It is why the patterns preserved in ancient light and the arrangement of galaxies billions of years later both align within the same framework. The same reasoning appears again when the story is told through a different kind of measurement. In the early universe, sound waves traveled through hot plasma, leaving behind a characteristic scale. That distance, how far those waves moved before the universe became transparent, acts as a cosmic ruler. Today, it appears as a subtle preference in how galaxies are spaced, a slight excess in the probability of finding pairs separated by about 150 megaparsecs. This imprint, known as baryon acoustic oscillations, links early plasma physics directly to the modern cosmic web. Its strength depends on the balance between atomic matter and dark matter, offering a powerful consistency check that does not rely on the same instruments or systematics as microwave background observations. Once again, independent data converge on the same conclusion. Now you can move inward, away from the largest scales, toward individual galaxies where the missing mass problem becomes intuitive. In a spiral galaxy, nearly all visible matter, stars and glowing gas, resides in a bright rotating disk. If gravity came only from what you can see, orbital speeds would rise near the center and then decline with distance, reflecting the enclosed mass. But observations tell a different story. Measured repeatedly through Doppler shifts, the rotation speeds of stars and gas remain nearly constant far beyond the luminous edge. This means mass continues to increase with radius even where light fades away. Gravity responds to something extended and substantial that cannot be seen. This pattern is not rare or delicate. It appears across galaxies of many sizes and environments, measured through optical spectroscopy, radio observations of hydrogen, and even in faint dwarf galaxies that contain little visible material yet remain strongly bound. Any alternative explanation must reproduce not a single curve, but an entire population trend. Rotation speeds correlate with galaxy mass and size. The inferred halos follow density profiles that closely resemble those produced in cold dark matter simulations. Could this missing component be ordinary matter hiding quietly? Cold gas, dim stars, dust, or compact objects? Each possibility has been tested. Gas reveals itself through spectral lines. Dust glows in infrared. Large populations of faint stars leave signatures in integrated light and chemical histories. Compact objects, if numerous enough, would alter microlensing statistics and produce gravitational effects inconsistent with smooth halos. While galaxies certainly contain hidden, ordinary components, attempts to fill the entire gap run into multiple independent limits long before the discrepancy disappears. At the scale of galaxy clusters, the tension grows stronger. These enormous systems contain vast reservoirs of gas heated to tens of millions of degrees, visible in X-rays. The temperature and distribution of this gas reveal the depth of the cluster's gravitational well. At the same time, clusters bend light from distant galaxies, producing arcs and subtle distortions. This gravitational lensing measures mass directly through spacetime curvature, regardless of whether that mass emits light. When these measurements are compared, hot gas plus galaxies versus total gravitating mass, the total is far larger. This pattern repeats across clusters and across cosmic time, making it difficult to attribute to error or coincidence. Lensing deserves special attention because it bypasses many intuitive objections. It responds only to gravity itself. When lensing maps show mass concentrations offset from luminous matter, gravity behaves as though matter exists where light does not. Wide-field weak lensing surveys reveal vast structures, an underlying framework more extended than visible galaxies. In this view, galaxies form inside halos rather than defining them. Clusters sit within even larger halos, with ordinary matter collecting into the gravitational landscape shaped by something unseen. It is natural to pause here and question whether this conclusion depends too heavily on Einstein's theory of gravity. That concern is reasonable, since interpretations of both microwave background data and lensing rely on general relativity. Yet the same pressure toward unseen mass arises from galaxy dynamics, cluster motions, and acoustic measurements, each probing the universe in different ways and carrying different uncertainties. Alternative gravity theories can reproduce certain galactic behaviors. The difficulty emerges when a single modification must explain everything at once. The precise peak structure of ancient radiation, the acoustic distance scale, the growth rate of structure, the lensing power spectrum, and the internal motions of clusters. Cold dark matter, by contrast, adds one new ingredient within an existing framework and brings many independent observations into agreement simultaneously. This is why the standard cosmological model settles where it does. It is not chosen for elegance, but because it allows diverse measurements to align within one coherent description. The model is often summarized by a small set of parameters, but what gives it strength is cross-checking. Early universe observations fix initial conditions. Galaxy surveys test clustering. Lensing traces mass directly. Local dynamics probe gravitational wells. When the same parameter values fit all of these within uncertainty, the picture becomes difficult to dismiss. The statement that less than 5% of the universe is familiar matter is not a slogan. It is a compact summary of an observational entanglement. Accept the measured radiation background. Accept the mapped distribution of galaxies. Accept gravity as the language connecting them. What follows is an enormous unseen sector, inferred not by belief, but by necessity. And yet, the story remains unfinished. While the gravitational influence of dark matter is measured with confidence, its physical nature remains unknown. Experiments searching for specific particles have not yet found a definitive signal. That absence does not weaken the evidence. It narrows the possibilities, guiding the search into new regions of mass and interaction strength. Even within the standard model, dark matter is more than extra weight. It sets the rhythm of galaxy formation. It governs how halos merge and how small galaxies survive. It shapes the quiet architecture on which visible structures slowly assemble. As you rest with this idea, the universe feels less empty, not more so. Filled with an unseen order that moves gently, patiently, holding everything in place as the night deepens and your thoughts grow still. It influences gravitational lensing statistics. When the universe tells us that most of its gravitating content is invisible, it is also telling us something deeper. The visible universe is a bright tracer layer, easy to photograph, but far too light to explain its own structure. Keep that in mind, because it determines how the next section unfolds. Once the cosmic census has been established using ancient radiation and large-scale clustering, attention turns to the most direct and consistently observed failure of visible matter gravity. When gravity is calculated using only the matter we can see, stars inside galaxies orbit as if the true mass extends far beyond the reach of any telescope. Part 2. Why would galaxies fly apart if we only count visible matter? If gravity within galaxies were produced solely by the stars and gas we observe, most galaxies would not survive more than a few rotations. Their outer regions would not remain bound. They would stretch, unravel, and disperse into intergalactic space. This is not metaphor or exaggeration. It follows directly from applying well-tested gravitational laws to measured motions inside real galaxies. The problem became clear when astronomers began measuring how fast stars move. In spiral galaxies, stars orbit the center along nearly circular paths. These speeds can be measured precisely by observing how starlight shifts toward red or blue as stars move away from or toward Earth. The method relies on basic atomic physics and has been used reliably for over a century. When such measurements were extended beyond the bright central regions of galaxies, the results revealed a serious conflict. According to Newtonian gravity, orbital speed depends on how much mass lies inside the orbit. Near the galactic center, where stars and gas are concentrated, speeds should rise with distance. Beyond the luminous disk, where little additional matter is visible, speeds should decline. This behavior works well in the solar system. Planets farther from the sun move more slowly because nearly all the mass is concentrated at the center. Galaxies were expected to behave the same way. They do not. Instead, stars far from the visible center continue to orbit at nearly the same speed as stars much closer in. These are known as flat rotation curves. The term sounds modest, but its implications are severe. A flat curve means that enclosed mass continues to increase with distance, even where almost no light is detected. Gravity behaves as if a massive, invisible component surrounds the galaxy in an extended halo. This behavior was not observed in a single object or survey. It appeared repeatedly as radio astronomy advanced and astronomers traced neutral hydrogen gas far beyond the optical edges of galaxies. Hydrogen emits radio waves at a wavelength of 21 centimeters, allowing astronomers to map gas where starlight is faint or absent. These gas clouds orbit at high speeds far outside the visible disk, and their motion cannot be explained by stellar gravity alone. One might suspect that the missing mass is simply ordinary matter that does not shine brightly. That possibility was examined carefully. Cold gas, faint stars, stellar remnants, and dust all leave detectable signatures. Gas emits spectral lines. Dust radiates in infrared. Even faint stars influence chemical abundances and integrated light. When these contributions are counted, the total mass increases, but nowhere near enough. The discrepancy remains large, often several times the mass of all visible components combined. At this point, the issue is no longer subtle. If only visible matter existed, the measured orbital speeds imply that stars should exceed escape velocity. They should drift outward and leave the galaxy. The fact that they do not means an additional gravitational component must be present. This conclusion does not depend on speculative physics. It follows directly from measured velocities and well-tested laws of gravity. The historical turning point came when systematic surveys replaced isolated measurements. Vera Rubin and her collaborators measured rotation curves across many spiral galaxies and found the same pattern again and again. The details varied, but the core result did not. The outer regions of galaxies move too fast. This behavior is not an anomaly, it is a defining property of spiral galaxies. This forced a shift in interpretation. Galaxies are not self-contained systems defined by their luminous matter. They are embedded within much larger gravitational structures. The visible disk is a tracer, not the primary source of gravity. The dominant mass extends far beyond the region where stars form. Independent evidence soon reinforced this picture. Elliptical galaxies, which lack clear rotation patterns, show unexpectedly high stellar velocity dispersions. Galaxy clusters exhibit internal motions far exceeding what visible matter can bind. In every case, gravity behaves as if more mass exists than can be seen. Gravitational lensing provides a different form of confirmation. Light from distant galaxies bends as it passes through gravitational fields. The amount of bending depends only on mass, not on whether that mass emits light. When astronomers map lensing around galaxies, they find mass distributions far larger and more extended than the visible components. The lensing signal traces halos enveloping galaxies, matching the mass required by rotation curves. These halos are not arbitrary. Their shapes and density profiles closely align with predictions from simulations that include cold dark matter. Those simulations begin with initial conditions measured from the cosmic microwave background and evolve forward under gravity. The halos that form naturally produce flat rotation curves without adjustment. Visible matter settles into disks within them, forming stars where conditions allow. Attempts to explain galaxy stability by modifying gravity itself have been explored. Some modified gravity models can reproduce flat rotation curves for certain galaxies, but they struggle to explain the full range of observations simultaneously. A model that fits spiral galaxies often fails for galaxy clusters or gravitational lensing. The difficulty is consistency across scales. Dark matter, by contrast, provides a single framework that works from dwarf galaxies to the largest bound structures in the universe. The evidence from galaxy stability marks a critical transition in cosmology. Before rotation curves were widely measured, dark matter was a hypothesis motivated by cluster dynamics. Afterward, it became a structural requirement. Galaxies as they exist require more gravity than visible matter can supply. Without that additional mass, their observed motions cannot persist. Modern observatories continue to refine this picture. High-resolution data from space-based and ground-based telescopes show that even low-mass galaxies with few stars are dominated by unseen mass. Some dwarf galaxies contain so little luminous matter that their dynamics are governed almost entirely by dark matter. This is difficult to reconcile with explanations based solely on ordinary matter. The James Webb Space Telescope extends this story into the early universe. It observes galaxies forming at epochs when there has been little time for complex processes to operate. Yet these young systems already show ordered rotation and significant mass. Their existence supports a scenario in which dark matter halos form first, creating gravitational wells that guide early galaxy assembly. The long-term stability of galaxies reinforces the conclusion. Spiral structures persist across billions of years. Stars complete many orbits without galaxies dissolving. Numerical models show that without dark matter halos, disks become unstable, bars grow too strong, and spiral patterns decay. The long-lived galaxies we observe require a stabilizing mass distribution extending far beyond the visible disk. This is why galaxy rotation curves represent one of the clearest and most direct pieces of evidence for dark matter. They rely on simple measurements of motion. They operate in a gravitational regime that is well tested. They reveal a discrepancy that cannot be eliminated by adjusting uncertain parameters. The result is robust. As Carl Sagan once noted, extraordinary claims require extraordinary evidence. In the case of dark matter, the evidence is not extraordinary because it is exotic. It is extraordinary because it is ordinary. Repeated measurements across countless systems pointing to the same conclusion. The claim arises because the universe behaves in a way that visible matter alone cannot explain. The idea that galaxies would fly apart without unseen mass is not a dramatic flourish. It is a literal statement of orbital mechanics. Remove the dark matter halo from a spiral galaxy, and the equations predict instability. Leave it in, and the equations match what telescopes observe. This realization reshapes how galaxies are understood. They are not isolated islands of stars drifting freely through space. They are luminous patterns traced onto massive, invisible frameworks. Light reveals the structure, but it does not define it. That understanding sharpens the narrative further. Once galactic motions reveal gravity extending beyond visible matter, attention shifts to environments where mass and light can be physically separated, situations where gravity can be traced independently of ordinary matter. That separation becomes unmistakable during violent collisions between galaxy clusters. Part 3. Why did Fritz Zwicky realize the universe was missing most of its mass? The first accusation that the universe was hiding most of its mass did not emerge from a modern control room filled with digital screens. It arose in the early 1930s, through handwritten calculations and photographic plates, when a single astronomer noticed that gravity was failing in a way that could not be quietly corrected. Galaxies within large clusters were moving so fast that, by every known rule of physics, they should not have remained bound at all. That astronomer was Fritz Zwicky, working at the Mount Wilson Observatory in California. At the time, galaxy clusters were still poorly understood. Astronomers knew galaxies existed in groups, but it was unclear whether those groups were temporary alignments or genuine gravitational systems. Zwicky approached the problem using a method that had already proven reliable elsewhere in astronomy. Measure motion, infer mass, and compare the two. He focused on the Coma cluster, a massive collection of thousands of galaxies located hundreds of millions of light-years away. Even by the standards of the time, the Coma cluster was extraordinary. Its galaxies were densely packed, and early observations already suggested unusually large internal motions. Zwicky began measuring the velocities of individual galaxies by examining how their spectral lines shifted due to motion along the line of sight. The results were immediately troubling. Galaxies in Coma were moving at velocities of several thousand kilometers per second. If the cluster's gravity came only from the visible galaxies, those speeds were far too high. According to Newtonian gravity, a system with such motions should disperse rapidly. The cluster should have flown apart long ago. Zwicky did not rely on qualitative impressions. He applied the virial theorem, a well-established principle that links the average kinetic energy of a gravitational system to its total gravitational binding energy. In simple terms, if the speeds of objects within a system are known, the total mass required to keep them bound can be estimated. When Zwicky carried out this calculation for the Coma cluster, the result was stark. The required mass was hundreds of times greater than the mass inferred from visible galaxies alone. This was not a small discrepancy that could be absorbed into uncertainty. It was a fundamental failure by orders of magnitude. Zwicky concluded that most of the cluster's mass was not emitting light. He referred to this missing component as dunkle materie, dark matter. In a 1933 paper, he wrote that the velocity dispersion observed in Coma demanded far more mass than was seen. The cluster behaved as if the visible galaxies were merely tracers moving within a much heavier, unseen structure. At the time, the astronomical community was not prepared to accept this conclusion. The idea that most of the universe's matter was invisible conflicted with intuition and prevailing assumptions. Observational techniques were still developing, and many assumed the discrepancy arose from underestimated luminosities, faint stars, or measurement errors. Zwicky himself was an unconventional figure, known for sharp criticism and uncompromising views, which did little to ease acceptance of his ideas. Yet the data remained. Galaxy velocities did not decline. The cluster did not disperse. And no plausible form of ordinary matter could fill the gap without revealing itself through other observations. What makes Zwicky's insight remarkable is not only that it was early, but that it was conceptually correct. He was not proposing exotic particles or speculative physics. He was following gravity where it led. If the motions were real and gravity behaved as understood, then mass was missing. The universe was acting as if most of its matter could not be seen. Decades later, as observational astronomy improved, the same problem reappeared independently. Other galaxy clusters showed similar discrepancies. Masses inferred from galaxy motions consistently exceeded luminous matter by large factors. This was no longer an isolated anomaly. It was a pattern. The case grew stronger as new observational tools emerged. X-ray astronomy revealed that galaxy clusters contain vast quantities of hot gas heated to tens of millions of degrees. This gas emits strongly in X-rays and contributes substantial mass. For a time, it appeared that this might resolve Zwicky's discrepancy. But when the gas mass was added to the galaxies, the gap closed only partially. The total gravitational mass still exceeded the visible mass by several times. Gravitational lensing later provided an entirely independent line of evidence. Light from background galaxies bends as it passes through the gravitational field of a cluster. The amount of bending depends only on total mass, not on whether that mass emits light. When astronomers mapped lensing in clusters, they found mass distributions consistent with Zwicky's original inference. Clusters are dominated by unseen matter. Modern observations leave little room for reinterpretation. Measurements from space-based observatories operated by NASA and the European Space Agency, combined with large ground-based surveys, consistently show that galaxy clusters are embedded within massive dark matter halos. These halos dominate the gravitational field and determine how galaxies move within clusters. The James Webb Space Telescope now extends this picture to earlier cosmic epochs. JWST observations reveal massive structures forming earlier than visible matter alone would allow. The gravitational scaffolding implied by Zwicky's work appears to have been present from very early times, shaping galaxy growth long before stars fully assembled. What Zwicky identified was not a peculiar property of coma. It was a general feature of gravity on large scales. Clusters are not loose gatherings of luminous galaxies. They are deep gravitational wells dominated by matter that neither emits nor absorbs light in any conventional way. In hindsight, resistance to Zwicky's conclusion is understandable. His claim challenged the assumption that light traces mass. For centuries, astronomy relied on brightness as a proxy for substance. Zwicky severed that connection. He showed that gravity, not light, was the more reliable guide. This shift carried profound consequences. Once clusters were understood to be dominated by unseen mass, galaxies themselves were reinterpreted. They became substructures within larger gravitational environments rather than self-contained systems. The concept of dark matter halos enveloping galaxies follows naturally from this cluster-scale insight. Zwicky's contribution also reshaped cosmology more quietly. It established that any serious model of the universe must account for gravitating matter beyond what is visible. This requirement now underpins modern cosmology. The nature of dark matter remains unknown, but its gravitational role was recognized long before particle physics entered the discussion. In 1976, long after his original work, Zwicky reflected on the resistance his ideas encountered. He noted that astronomers were often reluctant to accept conclusions that did not fit established frameworks. History ultimately sided with the data. The missing mass problem did not disappear. It expanded. Today, the evidence supporting Zwicky's insight comes from galaxy clusters across the observable universe, mapped through galaxy velocities, X-ray emitting gas, gravitational lensing, and numerical simulations. The conclusion is consistent and unavoidable. Most of the mass governing cluster dynamics is invisible. This realization carries the story into its next stage. If dark matter dominates galaxy clusters, and clusters are built from galaxies, attention must turn to how dark matter behaves when such structures collide at high speed. In some regions of the universe, clusters have passed directly through one another, leaving luminous matter displaced from the gravitational mass. In these environments, the separation is clear enough that the argument moves beyond indirect inference and into direct observation. Part 4. Why did Vera Rubin's data make dark matter impossible to ignore? The moment dark matter ceased to be a debatable hypothesis and became a structural requirement of cosmology arrived quietly, through repeated measurements that refused to change. Galaxies were rotating in ways no adjustment to visible matter could explain. Night after night, object after object, the data pointed to the same conclusion. At the center of this turning point was Vera Rubin. Working in the 1970s, her goal was simple and decisive. Measure how fast stars move at different distances from the centers of spiral galaxies with enough precision that uncertainty could no longer serve as an explanation. The expectation was clear. Newtonian gravity, which performs extraordinarily well in the solar system and in stellar binaries, predicts a specific pattern for orbital motion. When mass is concentrated near the center, orbital speeds rise in the inner region, peak, and then decline with distance. This is exactly what occurs around the Sun. Beyond a certain radius, little additional mass is present, gravity weakens, and velocities fall. Spiral galaxies were expected to follow the same logic. Their bright disks contain most of the visible stars and gas. Beyond the luminous edge, little matter is detected. If gravity were produced mainly by that luminous material, stars orbiting far from the center should move more slowly than those closer in. Rubin's measurements showed that this never happens. Using high-sensitivity spectrographs, Rubin and her collaborators measured Doppler shifts of stars and gas across galactic disks extending far beyond regions previously studied. What they found was not a subtle deviation. The rotation curves flattened. Stars tens of thousands of light-years from the center orbited at nearly the same speeds as those much closer in. The decline predicted by Newtonian gravity never appeared. Instead, the same pattern emerged again and again across galaxies. Large spirals, small spirals, isolated systems, and galaxies bound in groups all behaved the same way. The exact orbital speeds differed, but the defining feature remained unchanged. Once the visible disk ended, the rotation curve refused to drop. This behavior carried immediate implications. A flat rotation curve means that the mass contained within an orbit continues to grow roughly in step with distance from the center. Even as starlight fades rapidly, gravitational influence does not. Each galaxy behaves as though it is embedded within a vast, unseen halo extending far beyond its visible stars. At first, some hoped the discrepancy could be explained using familiar ingredients. Perhaps the outer regions were filled with dim stars. Perhaps cold gas stretched farther than expected. Rubin and her colleagues tested these possibilities directly. Observations across optical, radio, and infrared wavelengths tightly limited how much ordinary matter could remain hidden. Neutral hydrogen gas, mapped through its 21-centimeter emission, does extend beyond the stellar disk, but its total mass falls far short of what gravity demands. Dust and faint stellar populations also contribute, but only modestly. The gap was not small. In many galaxies, the mass inferred from rotation curves exceeded the visible mass by factors of 5 or more. No rearrangement of known baryonic components could close that gap without violating other well-established observational limits. What made Rubin's work decisive was not novelty, but reliability. Earlier hints of anomalous rotation existed, but they were scattered and often dismissed as experimental error. Rubin's surveys removed that uncertainty. The same flat curves appeared using different instruments, at different observatories, across different galaxy samples. The result persisted. Rubin herself described the outcome with characteristic restraint. She did not announce a new particle or propose a new force. She stated what the measurements required. As she later remarked, the universe contains more matter than we can see. The strangeness was not rhetorical. It followed directly from the mathematics of motion. The implications extended well beyond individual galaxies. If galaxies are surrounded by extended halos, then their interactions, mergers, and long-term stability depend on those halos. Numerical simulations soon confirmed this. When galaxies are modeled using only visible matter, their disks become unstable. Bars grow too strong, spiral patterns fade, and structure dissolves. When dark matter halos are included, galaxies remain stable for billions of years, matching what telescopes observe. Gravitational lensing provided an independent confirmation. Light from distant galaxies bends as it passes near massive objects. The degree of bending measures total mass directly. When astronomers mapped lensing around spiral galaxies, they found mass distributions extending far beyond the luminous disks, exactly as required by rotation curves. This convergence left little room for reinterpretation. Rotation curves, lensing measurements, and stability analyses all pointed to the same conclusion. Galaxies are not defined by their stars. They are bright components embedded within much larger invisible structures. The importance of Rubin's work lies in its clarity. It transformed an abstract discrepancy into a pattern visible throughout the nearby universe. Dark matter was no longer inferred only from distant clusters or ancient radiation. It was shaping the motion of stars in galaxies close enough to study in detail. Modern observations continue to strengthen this picture. Surveys supported by NASA and the European Space Agency show that rotation curves remain flat even in low-surface brightness galaxies where visible matter is scarce. In these systems, unseen mass dominates almost entirely. Their dynamics cannot be explained without it. The James Webb Space Telescope extends this evidence to earlier cosmic times. JWST observes rotating galaxies at high redshift when the universe was much younger. Even then, ordered motion and substantial mass are present, indicating that dark matter halos formed early and guided galaxy assembly from the beginning. Rubin's measurements also reshaped theories of galaxy formation. Stars form where gas cools and collapses, but gas collapses only where gravity allows. Dark matter halos supply the gravitational framework within which visible matter organizes. The luminous galaxy traces the potential well. It does not generate it. Attempts to replace dark matter with modifications of gravity continue, but they face a demanding standard set by rotation curves. Any alternative must reproduce not a single galaxy, but the systematic behavior across many systems, including the relationship between halo properties and luminous mass. So far, no alternative has matched the breadth of agreement achieved by dark matter models. The verdict that emerged from Rubin's work was not declared by consensus. It emerged because the data stopped offering escape routes. Flat rotation curves are easy to interpret and difficult to dismiss. They show gravity operating where light is absent. Carl Sagan once observed that science is not only compatible with spirituality, but a profound source of it. In this context, the idea takes a different form. Measurement revealed that the familiar universe is only a surface layer, and that most of what shapes cosmic motion lies beyond direct sight. This realization did not arise from speculation. It came from precise measurements of starlight shifting by tiny amounts. Dark matter halos appear around galaxies as stable, long-lived structures. Under ordinary conditions, they remain quiet and persistent. But when massive systems collide at high speed, those halos behave differently from luminous matter. In such events, gravity and light separate in ways that cannot be hidden. Part 5. Why can't dark matter be ordinary matter, antimatter, or black holes? If dark matter outweighs visible matter by such a large margin, an intuitive possibility immediately suggests itself. Perhaps it is not exotic at all. Perhaps it is made of the same substance as stars and planets, simply hidden from view. The idea is natural, appealing, and incorrect. The reason it fails is not philosophical. It is observational. The universe has been examined across the electromagnetic spectrum with increasing sensitivity for more than a century. From radio waves to gamma rays, ordinary matter leaves signatures. It emits, absorbs, scatters, heats, cools, ionizes, and recombines. Even when cold or diffuse, it interacts with radiation in measurable ways. If dark matter were simply ordinary matter arranged differently, those interactions would already appear in the data. Consider the most straightforward candidate: normal matter that does not shine. Gas clouds, faint stars, brown dwarfs, stellar remnants, cold planets drifting between stars. Early dark matter research grouped these possibilities under the term MACHOs, massive, astrophysical compact halo objects. They seemed promising because they are massive and dim. But gravity alone does not allow them to remain hidden indefinitely. A halo dominated by compact objects would reveal itself through gravitational microlensing. As such objects pass in front of background stars, they briefly magnify the starlight. Large surveys were designed to detect these events. The outcome was unambiguous. Microlensing does occur, but far too infrequently for machos to account for more than a small fraction of dark matter. They cannot dominate halos without violating observed statistics. Diffuse gas performs no better. Gas emits radiation as it cools, particularly in radio, infrared, and X-ray wavelengths. Large quantities would alter galaxy spectra, produce emission lines, and affect star formation histories. Observations tightly constrain how much unseen gas can exist. It is present, but nowhere near enough. Cosmology reinforces this conclusion. The cosmic microwave background does not merely measure total matter. It distinguishes between matter that interacts with radiation and matter that does not. Ordinary matter couples strongly to photons in the early universe, leaving a clear imprint on the microwave background. Dark matter does not. The relative heights of the acoustic peaks measured by missions such as Planck require a specific ratio between baryonic and non-baryonic matter. Increasing ordinary matter beyond that ratio breaks the agreement with observations. Another possibility follows naturally. Antimatter. Antimatter has mass and responds to gravity. Could it serve as dark matter? The answer is no. When antimatter encounters matter, the two annihilate, producing gamma rays with well-defined energies. Astronomers have mapped the gamma ray sky in detail. If large quantities of antimatter were present in galactic halos, annihilation signatures would appear where matter and antimatter met. They do not. For antimatter to avoid annihilation, it would need to be segregated into vast, isolated regions, separated from normal matter by enormous distances. Such segregation would leave other observable signatures, including distortions in large-scale structure and characteristic gamma-ray backgrounds. These are not observed. The universe behaves as though antimatter exists only in small amounts produced in high-energy processes, not as a dominant mass component. This leaves one of the most dramatic candidates: black holes. Black holes are massive. They interact gravitationally. They emit no light directly. On the surface, they seem to satisfy several requirements. This idea has resurfaced repeatedly, most recently in discussions of primordial black holes formed in the early universe. Here again, observations impose sharp limits. A halo composed largely of black holes would not behave smoothly. Black holes interact violently through gravity. They would scatter stars, heat galactic disks, and disrupt delicate structures. The thinness and long-term stability of galactic disks strongly restrict how much mass can be locked into compact objects. Gravitational lensing provides further constraints. A halo made of compact objects would produce lensing signatures different from those observed. Instead of smooth distortions, astronomers would detect frequent sharp events. Large surveys do not show this pattern at the required level. There is also the question of mergers. Black holes merge, emitting gravitational waves. The rate of such events is now measured directly by observatories like LIGO and Virgo. The observed merger rates are incompatible with a universe in which most dark matter consists of black holes in the mass ranges allowed by other constraints. Primordial black holes are not ruled out entirely, but they are tightly restricted. Under specific conditions, they may contribute a fraction of dark matter. They cannot dominate without conflicting with multiple independent observations. Each proposed explanation for the missing mass follows the same path. A possibility is introduced. Its gravitational influence is examined. Then its unavoidable secondary effects are compared with observation. Ordinary matter emits radiation. Antimatter annihilates. Compact objects merge, heat their surroundings, and leave detectable traces. Whatever dark matter is, it does none of these things at observable levels. This progressive elimination is not a lack of creativity. It is the disciplined logic of science. As Carl Sagan once observed, it is preferable to understand the universe as it truly is than to cling to comforting illusions. Familiar answers feel safe. The cosmos offers no such reassurance. What survives this process is not a known substance but a set of requirements. Dark matter must emit little or no light. It must interact only weakly with electromagnetic radiation. It must remain stable across billions of years. It must cluster gravitationally into vast halos, and it must have existed early enough to guide the formation of cosmic structure. These conditions rule out conventional astrophysical objects and instead point toward new forms of matter. Hypotheses such as weakly interacting massive particles, axions, sterile neutrinos, and other exotic candidates arise not from fashion, but from constraint. They remain viable because they satisfy everything the universe demands and nothing it forbids. Experiments pursue these possibilities on multiple fronts. Deep underground detectors watch for rare interactions between dark matter and atomic nuclei. Telescopes search for faint signatures from annihilation or decay. Particle accelerators explore energy regimes where new physics might reveal itself. So far, none has delivered a definitive detection. Yet, absence of detection is not absence of influence. The gravitational evidence remains overwhelming. Observations from the James Webb Space Telescope reinforce this conclusion indirectly. JWST reveals galaxies forming earlier than expected, assembling mass rapidly, and organizing into rotating systems soon after the universe began. These findings align naturally with models in which dark matter creates gravitational wells long before ordinary matter can cool, collapse, and ignite stars. They do not align with scenarios in which visible matter alone dominates the mass budget. What makes this phase of the argument compelling is its restraint. Dark matter is not introduced casually. It persists because alternatives fail under scrutiny. Every familiar form of matter leaves signatures that are not observed at the required scale. Dark matter remains because it alone satisfies all known constraints simultaneously. This does not mean the mystery is solved. It means the problem is sharply defined. The universe has told us what dark matter does not do. It has revealed how dark matter behaves gravitationally. It has shown when dark matter must have existed. What remains unknown is its microscopic nature. Dark matter does not collide like gas. It does not heat or radiate like plasma. These differences become most visible not in calm galactic rotation, but during violent cosmic encounters. In collisions between massive systems, luminous matter slows, compresses, and shines, while the gravitational mass continues forward almost unaffected. In such events, gravity and light visibly diverge. Part 6. Why does bent light reveal mass where nothing shines? Light does not curve on its own. Yet throughout the universe, it arrives distorted, stretched, and displaced in patterns that betray the presence of gravity where no luminous matter exists. This phenomenon is not inferred indirectly. It is measured repeatedly, directly, and with increasing precision. Long before dark matter could be simulated or searched for in laboratories, light itself began tracing maps of mass that stars and gas could not explain. The foundation for this effect was laid in the early 20th century, when Albert Einstein showed that gravity is not merely a force, but a curvature of spacetime. In this framework, light follows the geometry of space itself. When spacetime is warped by mass, photons change direction. The implication is unavoidable. Any mass, whether bright or dark, bends light passing nearby. This prediction was first confirmed during the solar eclipse of 1919, when starlight grazing the sun was observed to shift exactly as Einstein's equations predicted. From that moment onward, gravitational lensing became more than a test of theory. It became a tool. If light responds to mass, then measuring its deflection reveals mass directly, independent of luminosity. Gravitational lensing occurs when light from a distant galaxy passes near a foreground mass on its journey to Earth. The intervening mass acts as a lens, altering the apparent position and shape of the background object. When alignment is precise and mass is large, as in galaxy clusters, the effect is dramatic. Galaxies are stretched into arcs, rings, or multiple images. This is strong lensing. More often, the effect is subtle. The shapes of background galaxies are distorted by only a few percent, coherently across wide regions of sky. This is weak gravitational lensing. No single galaxy reveals the signal clearly, but when millions are analyzed statistically, a detailed map of intervening mass emerges. Crucially, this map traces total mass, not just what shines. Here lensing becomes decisive. When astronomers reconstruct mass distributions from lensing data, they do not recover the same patterns seen in visible light. Instead, they uncover extended halos of mass surrounding galaxies and clusters, often reaching far beyond luminous boundaries. These halos match the distributions required by galaxy rotation curves and cluster dynamics, yet they do not coincide with stars or gas alone. The power of lensing lies in its independence. It does not rely on assumptions about stellar motion or gas temperature. It does not require systems to be in equilibrium. It depends only on how spacetime bends light. In this sense, lensing probes gravity itself. Large surveys conducted by space-based observatories and ground-based telescopes have mapped weak lensing across vast regions of the sky. The results are consistent and striking. Most of the universe's mass does not follow the distribution of light. Dark matter halos appear smoother and more extended than luminous matter. Stars clump tightly. Gas cools and condenses. Dark matter spreads into broad, roughly spherical halos that dominate gravitational structure. Lensing traces these halos directly. In many systems, the strongest lensing signal arises where few stars and little gas exist. This pattern repeats across scales. Individual galaxies exhibit lensing far beyond their visible disks. Groups of galaxies share common halos. Clusters contain mass concentrations that dwarf the combined mass of their galaxies. In every case, lensing agrees with dynamical mass estimates and contradicts predictions based on visible matter alone. This consistency is not accidental. Lensing observations align closely with simulations that include cold dark matter. When dark matter is present, simulated universes reproduce observed lensing patterns. When it is removed, they do not. An important conclusion follows. Gravitational lensing is indifferent to the nature of dark matter. It responds only to mass and spacetime curvature. It cannot be biased by assumptions about radiation, chemistry, or stellar evolution. It is a neutral witness. The James Webb Space Telescope extends this testimony deeper into cosmic history. JWST observes distant galaxies magnified and distorted by intervening mass, allowing detailed study of both background sources and foreground lenses. In many cases, the lensing mass is dominated by dark matter halos already established when the universe was young. This early presence is critical. If dark matter formed late, lensing signals would evolve differently with redshift. Instead, they show that large-scale mass structures were in place from the beginning, guiding galaxy growth. Weak lensing surveys also test cosmological models statistically. By measuring how mass clusters across scales, astronomers compare observations with predictions from the Lambda CDM framework. The agreement is strong. Both the strength and scale dependence of lensing signals match expectations for a universe dominated by dark matter. Alternative explanations face a formidable challenge here. Any modification of gravity must reproduce not only galaxy rotation curves but also lensing patterns across cosmic scales. Because lensing responds directly to spacetime curvature, such theories must alter both motion and light deflection consistently. Many proposals struggle to do so without reintroducing unseen components in another form. Strong lensing adds a geometric constraint. The precise positions and shapes of multiple images tightly restrict the mass distribution. Often, the required mass lies where little or no luminous matter exists. The geometry leaves little freedom. The mass must be present, or the images would not appear as they do. This is why gravitational lensing transformed dark matter from an abstract inference into something nearly visual. Though it cannot be photographed, its gravitational imprint can be traced with clarity. The universe reveals mass without light by showing how light itself is guided. As Carl Sagan emphasized, Independent lines of evidence are essential. In gravitational lensing, that principle is fully realized. The same dark matter halos inferred from galaxy rotation appear again in lensing maps derived from entirely different physics. The agreement is not superficial. It is structural. Light reaches us bent in patterns that correspond to invisible mass distributions across the universe. These structures are coherent, persistent, and stable. They do not flicker like luminous matter. They form a gravitational framework upon which everything else is built. Lensing reveals mass even in tranquil systems, but its power becomes unmistakable during extremes. When massive systems collide, ordinary matter slows, heats, and radiates, while dark matter passes through with little resistance. In these rare events, lensing exposes a separation so stark that mass and light visibly part ways. Part 7. Why did the bullet cluster separate mass from matter so cleanly? There exists a place in the universe where gravity and light diverged so clearly that doubt itself was forced to retreat. Not through interpretation or statistical subtlety, but through a collision so extreme and so clearly observed that mass and ordinary matter ended up separated on the sky. This event is known as the bullet cluster, and its importance lies in how directly it reveals the nature of dark matter. The bullet cluster is not a single object, but the aftermath of a high-velocity merger between two galaxy clusters. Galaxy clusters are the largest gravitationally bound systems in the universe. Each contains thousands of galaxies, enormous reservoirs of superheated gas, and an even greater quantity of unseen mass. When two such systems collide, their components respond in fundamentally different ways. Galaxies themselves are mostly empty space. During the collision, individual galaxies pass by one another without significant interaction. They behave almost as if nothing were there, continuing forward largely unaffected. The hot gas tells a different story. This gas accounts for most of the ordinary, baryonic matter in galaxy clusters. Though thin, it fills the space between galaxies. When clusters collide, their gas clouds interact directly. They slow, compress, and heat to tens of millions of degrees, producing intense X-ray radiation. The third component behaves differently from both. Whatever dominates the gravitational mass of the clusters does not emit light, does not heat up, and does not slow down during the collision. In the bullet cluster, this dominant mass component passed through almost untouched. This separation was captured with exceptional clarity. X-ray observations revealed a bright, shock-heated cloud of gas lagging behind the galaxies, slowed by the collision. Optical images showed the galaxies continuing ahead. Gravitational lensing measurements then reconstructed the total mass distribution. The result was unambiguous. The lensing signal did not peak where the hot gas was concentrated. It peaked where the galaxies were. This is the critical observation. Most of the mass was not located where most of the ordinary matter resided. The lensing maps revealed two dominant mass concentrations aligned with the galaxies rather than the X-ray, bright gas. Although the gas contained the majority of the baryonic matter, it did not dominate the gravitational field. Gravity traced something else entirely. This matters because it removes ambiguity. In relaxed systems, debates can arise about equilibrium, modeling assumptions, or hidden uncertainties. The bullet cluster is neither calm nor balanced. It is violent, transient, and far from equilibrium. The separation between gas and mass is physical and direct. If gravity were produced primarily by ordinary matter, the lensing signal would peak at the gas clouds. It does not. If gravity were modified universally without unseen mass, the lensing signal would still follow the baryonic matter. It does not. Instead, the gravitational field follows the galaxies, not the gas. This behavior is exactly what is expected if most of the mass is non-collisional. Dark matter interacts gravitationally, but not through the electromagnetic forces that cause gas to collide, compress, and radiate. In the bullet cluster, the dark matter halos of the two original clusters passed through one another while the gas collided and stalled. The result is a clean spatial offset between mass and ordinary matter. This conclusion did not arise from a single observation. The bullet cluster was studied extensively across multiple wavelengths and instruments. X-ray data from NASA-operated observatories mapped the temperature and density of the gas. Optical imaging and spectroscopy traced galaxy positions. Weak gravitational lensing independently reconstructed the mass distribution. Each dataset converged on the same result. What makes this case particularly powerful is that the conclusion does not depend on detailed modeling of the collision. Gravitational lensing responds only to spacetime curvature. It does not depend on assumptions about composition or dynamics. The fact that the lensing peaks are displaced from the gas peaks is a geometric fact on the sky. The bullet cluster was not unique. Other merging clusters have since been observed showing similar separations. Each adds weight to the same conclusion. The bullet cluster stands out because the geometry is favorable, the separation is large, and the data quality is exceptional. Alternative explanations were examined. Could gas physics be misunderstood? Could projection effects be misleading? Detailed analyses addressed these possibilities. The separation persists under different assumptions. The lensing signal remains robust. The mass simply does not coincide with the ordinary matter. This observation places important constraints on dark matter itself. It shows that dark matter is not only invisible, but effectively collisionless on cluster scales. If dark matter particles interacted strongly with one another, the dark matter halos would have slowed or deformed during the collision, much like the gas. They did not. The halos passed through with minimal disturbance. This limits how strongly dark matter particles can interact with each other. In this sense, the bullet cluster is not merely evidence for dark matter's existence. It functions as a natural experiment, probing its physical properties. The implications extend beyond cluster mergers. Models of cosmic structure formation assume that dark matter can stream through itself and through ordinary matter with little interaction. The bullet cluster confirms that assumption in one of the most extreme environments available. It also sharpens the distinction between dark matter and explanations based solely on modified gravity. In this system, gravity itself is displaced from baryonic matter. The lensing signal follows something that behaves like matter but does not interact like matter. This is difficult to reconcile with gravity-only theories. For this reason, space agencies and research institutions have described the bullet cluster as one of the clearest empirical demonstrations of dark matter. The term direct is used carefully. Dark matter is not seen, but its gravitational effects are spatially separated from all known forms of ordinary matter. That separation is observed, not inferred. The bullet cluster does not stand alone. Galaxy rotation curves reveal missing mass. Lensing reveals mass without light. The bullet cluster reveals mass where matter is not. Together, these lines of evidence converge. There is also a human dimension to this discovery. It required coordination across disciplines and instruments. X-ray astronomers, optical observers, and gravitational lensing specialists combined their expertise. No single method would have been sufficient. Clarity emerged through convergence. The universe occasionally provides experiments far beyond anything humanity can construct. Two galaxy clusters collided at thousands of kilometers per second, heating gas to tens of millions of degrees while leaving dark matter largely unaffected. Nature performed the experiment. Astronomers recorded the outcome. This collision did not create dark matter. It revealed how dark matter behaves under extreme conditions. It showed that dark matter is not another form of gas or dust. It does not slow, heat, or shine. It responds to gravity and little else. The lesson carries forward. Future observations of similar systems can further constrain dark matter properties. Variations in separation, halo deformation, or interaction signatures may narrow the range of viable particle models. The bullet cluster occupies a central place in the story not because it answers what dark matter is, but because it defines what dark matter is not. It is not ordinary matter. It is not strongly interacting. It is not bound to light. Dark matter shapes gravity on the largest scales, forming a smooth, non-dissipative framework for cosmic structure. Its influence does not stop within galaxies or clusters. On the largest scales of all, it intersects with another phenomenon that governs the universe globally rather than locally. Their spectra show redshifts far larger than those Hubble originally measured, consistent with a universe that has been expanding for nearly its entire history. The light from these distant galaxies is stretched not because the galaxies themselves are moving unusually fast, but because space has continued to expand while the light was traveling. The stretching accumulates over billions of years, imprinting expansion directly onto the light itself. This perspective resolves a common misunderstanding. In an expanding universe, distant galaxies can appear to recede faster than the speed of light without violating relativity. The reason is simple but subtle. The galaxies are not moving through space faster than light. Instead, the space between them and the observer is expanding. General relativity allows this, and observations confirm it. Hubble's discovery also transformed how gravity is understood on cosmic scales. In a static universe, gravity would eventually pull matter together. In an expanding universe, gravity must compete with expansion. The balance between these two influences determines the evolution of cosmic structure. For decades, astronomers assumed that expansion should gradually slow as gravity worked against it. The question became quantitative. How much mass exists in the universe, and is it sufficient to halt or reverse expansion? That question leads directly to a later and far more surprising discovery. Expansion is not slowing down at all. It is accelerating. That conclusion requires the existence of dark energy. But it rests entirely on Hubble's original insight that expansion exists in the first place. What gives Hubble's work its enduring power is its simplicity. He did not begin with a theory of cosmic origin. He measured distances. He measured redshifts. He compared them. The universe responded with a pattern. Hubble himself remained cautious in interpretation, initially describing a redshift distance relation without committing to a specific cosmological model. But the data left little room for alternatives. Over time, independent confirmations removed the remaining doubt. Radio astronomy, infrared surveys, optical spectroscopy, and space-based observations all converged on the same conclusion. The universe is expanding. This result does not come from a single era or a single method. It is measured continuously across cosmic time. This realization also reshaped humanity's place in the cosmos. There is no central vantage point. Every galaxy sees others receding. Expansion does not privilege location. It is a property of space itself. As Carl Sagan often emphasized, science advances by replacing comforting assumptions with measured reality. Hubble's work did exactly that. It replaced the idea of an eternal, unchanging universe with one that is dynamic, evolving, measurable, and finite in age. Cosmic expansion is now one of the foundational facts of cosmology. It underlies the Big Bang framework, the interpretation of the cosmic microwave background, and the formation of large-scale structure. Without Hubble's redshift measurements, these later developments would lack empirical grounding. Yet the story does not end with expansion alone. Once expansion was established as fact, a deeper question followed naturally. If space is expanding under the influence of gravity, what determines whether that expansion slows, stops, or accelerates? Decades later, observations revealed something unexpected. On the largest scales, space is being pushed apart rather than pulled together. This conclusion did not emerge from Hubble's early work. It arose when astronomers began using distant stellar explosions as direct probes of cosmic expansion over time. Part 9. Why did the universe begin expanding faster instead of slowing down? For most of the 20th century, astronomers believed they understood how cosmic expansion should behave. Once expansion was observed, gravity was expected to slow it down. Every galaxy, every cluster, every particle carries mass, and mass attracts mass. Over billions of years, that attraction should reduce the expansion rate. The universe might expand forever or eventually collapse, but acceleration was not expected. That expectation was grounded in theory, observation, and intuition. And it was wrong. The first indication came not from theory, but from an attempt to measure cosmic history directly. In the 1990s, two independent research teams set out to answer a practical question. How fast was the universe expanding in the past compared to now? If gravity were slowing expansion, distant objects would carry a measurable signature of that deceleration. The tool chosen was a specific type of stellar explosion known as a Type Ia supernova. These events occur when a white dwarf star accumulates matter from a companion until it reaches a critical mass and detonates. What makes Type Ia supernovae valuable is their consistency. They reach nearly the same intrinsic brightness each time. By comparing how bright they appear with how bright they are known to be, astronomers can determine distance. This method rests on well-understood physics. The light curves of Type Ia supernovae, the way their brightness rises and fades, follow a characteristic pattern. Small variations can be corrected using empirical relationships, tightening distance estimates. By the 1990s, these techniques were reliable enough to probe billions of light-years into the past. Two teams led the effort. One was the Supernova Cosmology project, led by Saul Perlmutter. The other was the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees. Their goal was not to overturn cosmology, but to measure how much the expansion of the universe had slowed. The expectation was clear. If gravity dominated, distant supernovae should appear brighter than they would in a universe expanding at a constant rate. That brightness would indicate faster expansion in the past and gradual deceleration since then. The teams collected data carefully, calibrating instruments and checking for systematic errors. They observed supernovae at redshifts corresponding to billions of years ago. What they found was the opposite of expectation. Distant Type Ia supernovae were dimmer than predicted. Not marginally, not ambiguously, but consistently. The data indicated that the universe was expanding more slowly in the past than it is today. Expansion was not decelerating. It was accelerating. This result was unsettling for a simple reason. There was no known mechanism to explain it. Gravity pulls. It does not push. Ordinary matter and dark matter both contribute positive gravitational attraction. Neither can produce acceleration on cosmic scales. The teams scrutinized every possible alternative. Could distant supernovae be intrinsically dimmer? Could dust be absorbing light and mimicking acceleration? Dust leaves wavelength-dependent signatures. The observed spectra did not show them. Could supernova properties evolve over time? Nearby and distant events followed the same corrected light curve relations. Independent datasets confirmed the trend. As the sample grew, the conclusion strengthened. The expansion of the universe is accelerating. To explain this, cosmologists were forced to introduce a new component with an unusual property. It must exert negative pressure on large scales. In general relativity, pressure contributes to gravity. Negative pressure can drive accelerated expansion. This component became known as dark energy. The simplest form of dark energy corresponds to the cosmological constant, originally introduced by Einstein and later abandoned. In this interpretation, empty space itself carries energy. As space expands, the total amount of this energy increases, driving further expansion. Dark energy behaves very differently from matter. It does not clump. It does not form structures or halos. It remains nearly uniform as space grows. This explains why its influence becomes dominant only at late times. In the early universe, matter density was high and gravity slowed expansion. As matter thinned, dark energy remained constant per unit volume and eventually took over. The supernova results did not stand alone for long. Measurements of the cosmic microwave background constrained the geometry of the early universe. Large-scale galaxy surveys mapped how structure grew over time. Together, these independent lines of evidence converged on the same conclusion. Today, the universe is dominated by dark energy. Observatories operated by NASA and the European Space Agency played central roles in confirming this picture. Satellite missions measured background radiation with extraordinary precision. Ground-based surveys mapped galaxy distributions and baryon acoustic oscillations, providing independent distance scales. The James Webb Space Telescope now extends these tests to earlier epochs, observing galaxies before dark energy dominated cosmic dynamics. So far, all results remain consistent with an accelerating universe. What makes the supernova discovery especially powerful is its directness. It does not rely on assumptions about equilibrium or structure formation. It uses standardized cosmic explosions as mile markers across time. The universe itself provides the timeline. In 2011, the significance of this discovery was formally recognized when Saul Perlmutter, Brian Schmidt, and Adam Rees were awarded the Nobel Prize in Physics. The citation emphasized the unexpected nature of the result. Acceleration was not predicted, it was observed. This acceleration has profound consequences. It determines the ultimate fate of the universe. If dark energy remains constant, galaxies beyond a certain distance will eventually recede faster than light can bridge. Structures that are not gravitationally bound will drift out of contact. The large-scale universe will grow increasingly isolated. Yet, despite its influence, dark energy remains deeply mysterious. Unlike dark matter, which leaves fingerprints in galaxy rotation and gravitational lensing, dark energy reveals itself only through its effect on cosmic expansion. It does not cluster. It does not emit or absorb light. Its presence is inferred indirectly through precise measurements of cosmic distances and redshifts. The supernova discovery did not tell us what dark energy is. It told us that something new must exist. The universe's expansion history cannot be explained by matter alone. As Carl Sagan often reminded us, science advances by following the evidence, even when it leads to uncomfortable truths. The acceleration of the universe is one of those truths. It tells us that the dominant component of the cosmos acts not by pulling matter together, but by driving space itself apart. This realization completes a pattern established over previous discoveries. Dark matter explains why galaxies and clusters hold together. Dark energy explains why the universe as a whole continues to expand. Together, they dominate cosmic behavior, while ordinary matter plays only a supporting role. Yet the picture remains incomplete. Dark energy accounts for roughly 68% of the universe's total energy budget, but its nature is unknown. Is it truly constant, or does it evolve over time? Is it a property of space itself, or evidence of new physics beyond general relativity? These questions do not arise from speculation. They arise because precise measurements forced a conclusion that theory had not anticipated. Dark energy outweighs all matter combined. It governs the expansion of space itself. Yet it leaves no trace in laboratories, no signal in telescopes, no particle track in detectors. Its existence is inferred only because the universe behaves in a way that cannot be explained without it. The simplest explanation is the cosmological constant, first introduced by Einstein and later abandoned. In this interpretation, empty space carries energy. As the universe expands, the total amount of this energy increases, driving further expansion. Matter thins over time, but dark energy remains constant per unit volume. Its influence grows until it dominates, as it does today. This explanation fits observations, but it raises a deeper problem. Quantum field theory predicts the energy of empty space to be vastly larger than what is observed, by more than 100 orders of magnitude. This mismatch is often called the worst prediction in physics, highlighting a tension between gravity and quantum mechanics that remains unresolved. Alternative models propose that dark energy might be dynamic, changing over time, or that our understanding of gravity breaks down on cosmic scales. So far, observations, from supernovae to the cosmic microwave background, from galaxy surveys to the James Webb Space Telescope, show no clear deviation from a constant dark energy. What makes dark energy so difficult to study is its smoothness. Unlike dark matter, it does not clump. It leaves no local structures to map. Its presence is revealed only statistically, through its cumulative effect on expansion. Every piece of evidence comes indirectly. Distances to supernovae, patterns in background radiation, galaxy clustering. None relies on a single observation. The conclusion emerges because independent methods converge. This is why dark energy is both reassuring and troubling. It confirms that our cosmological framework works extraordinarily well. Yet the dominant component of the universe remains unexplained. Dark energy is the name we give to whatever causes cosmic acceleration. It is a description, not an understanding. Its implications are profound. If dark energy remains constant, the universe will continue to expand at an accelerating pace. Distant galaxies will drift beyond observational reach. Star formation will slow as matter becomes increasingly isolated. These outcomes follow directly from the measured properties of dark energy, not from speculation. Yet uncertainty remains. Observations continue to improve. New surveys aim to map the expansion history with unprecedented precision. Small deviations from constancy could reveal new physics. Alternatively, the cosmological constant may persist, forcing theorists to confront the vacuum energy problem head-on. Dark energy links the largest scales of the universe to the smallest. The behavior of empty space over billions of light-years may depend on quantum processes at subatomic scales. Nothing else in nature connects extremes in this way. Dark energy is not just another cosmic component. It is a signpost pointing toward what we do not yet understand. It shows that our framework for nature works extraordinarily well, but not completely. Current observations are clear. Most of the universe is invisible. Gravity does not follow the patterns expected from visible matter alone. Space itself carries energy with measurable consequences. These conclusions come directly from data, even as the deeper explanation remains unknown. Measurements will continue. Independent surveys will refine the picture, and the universe will continue to expand, regardless of how quickly our understanding advances. Thank you for spending this time with Scientist Stories. Your attention and patience are deeply appreciated. Wherever you are, and whatever hour has brought you here, may the rest of your night be peaceful. May sleep come easily, with the quiet reassurance that knowledge grows through careful observation, step by step.